Today's topic is the Otto cycle. Otto cycle is an ideal thermodynamic cycle which makes your gasoline-fueled car to move and speed up by performing a 4 piston strokes of the car's engine. So to understand the strokes of this cycle, let us first name the key terms for this topic. First is the cylinder, the space to which the piston travels up and down. Top dead center, farthest point of the piston's upward travel. Bottom dead center, farthest point of the piston's downward travel. Stroke. This is what we call when the piston travels from bottom dead center to top dead center or vice versa. Intake valve introduces the air and gasoline mixture into the cylinder. Exhaust valve evacuates the unburned gases from the cylinder. Spark plug provides heat energy by its spark. And finally, piston, the one that converts the heat energy from the combustion into mechanical energy that will rotate the car's wheels. So now, we are ready for our main event, the 4 strokes. And here, our intake valve is open, and this is what we call the intake stroke. Piston travels downward from top dead center to bottom dead center to draw the air and gasoline mixture into the cylinder. So as you can see, the volume increases. Next is the second stroke. Piston travels upward to compress the air and gasoline to make it a combustible mixture. So since this is the compression, and as you can see it clearly, the volume decreases and the pressure increases. This is called the compression stroke. Before moving to the third stroke, we will need something to give us power, and that is where the combustion comes in. Here, the spark plug now ignites, provides heat to the fuel and oxygen, which will produce combustion. The combustion is what we call the heat addition to our engine, and of course, the pressure increases. Now, we can move to the third stroke by utilizing that heat energy from the combustion. So here, the pressure now decreases and the volume increases, and this stroke is what we call the power stroke. It's called as the power stroke as this is the power that moves your car and will keep the cycle from going around. Now, after using the air and fuel mixture, its waste will now need to be evacuated. This is what we call the heat rejection of our engine. The exhaust valve is open to assist the evacuation of the waste gases from the cylinder, making the pressure to decrease. And finally, the last stroke. The last stroke will now be used as we need something to evacuate the waste gases out. The piston will now travel upward to push out the waste gases, and this is what we call the exhaust stroke.
Hi, my name is Dayana Albano and my metric number is 60613. In this part, I'll be talking about the engine parameters. As can be seen in the slide, these are the parameters that can be determined through the formula shown. The stroke length is typically denoted as capital S or capital L as shown in the formula and in diagram 1. The connecting rod is also denoted as small l or small r. The crank angle, which is represented by theta, is measured from the cylinder center line and is equivalent to 0 when the piston is at the top dead center. The instantaneous piston velocity can be determined by differentiating the distance s, which is the distance between the crank axis and wrist pin with respect to time. The ratio between the connecting rod length to the crank offset can be denoted as capital R. The graph shows the effect of R on the piston speed. A good indicator of an engine ability to do work can be represented by its torque, and the rate of work of the engine is known as power. The power can also be defined as brake power or indicated power depending on the definition of work or mean effective pressure used in calculating the power. Brake power is the amount of power measured at the output shaft, whereas the indicated power is the power produced in the cylinder. Generally, the brake power is lower than the power generated by the gas in the cylinders due to the mechanical friction and parasitic loads.
Hello, my name is Cynthia Bong, metric number 60588. Today I'm going to be the second presenter for our group. What is indicator? Indicator consists of pressure indicator, crank angle encoder, and also tachometer. The purpose of indicator is to obtain pressure inside cylinder. From there, we can produce PV diagram, which also known as indicator diagram of in-cylinder gas. All parameters 10 from indicator diagram has prefix indicated, where in this part we're going to explain on indicated work per cycle, indicated power, indicated work at part throttle, and also indicated work with supercharging. For early indicator diagram, it were generated by mechanical plotter linked directly to the engine, whereas for modern PV indicator diagram, it are generated on an oscilloscope using pressure transducer mounted in the combustion chamber and an electronic position sensor mounted on the piston or crankshaft. As shown is the indicator diagram, where the engine cycle is plotted on the PV coordinate. For the first part is indicated work per cycle. Pressure data for the gas in the cylinder over the operating cycle of the engine can be used to calculate the work transfer from the gas to the piston. The cylinder pressure and corresponding cylinder volume throughout the engine cycle can be plotted on PV diagram. Work in this scenario is defined as the output of any heat engine and in a reciprocating IC engine. This work is generated by the gases in the combustion chamber of the cylinder. This results from a force acting through a distance. This force due to gas pressure on the moving piston generates the work in an IC engine cycle. As shown is the formula, where W is equal to the integration of PA dx, where P is the pressure in combustion chamber, A is the area against which the pressure acts, and X is the distance the piston moves. And as A dx is equal to dV, where dV is the differential volume displaced by the piston, so work done can be written as W equal to the integration of P dV. The indicated work per cycle is given by W equal to P times V, and the displacement volume, which is V, is equal to A times L times N, where A is the cylinder cross-section, B is the bore diameter, L is the stroke length, and N is the number of cylinders. As shown in the diagram, the upper loop of the engine cycle consists of compression and power stroke, where output work is generated and is called the gross indicated work, which includes the area of A and C. The lower loop, which includes the intake and exhaust stroke, is called pump work and absorbed work from the engine, which includes the area of B and C. Whereas for net indicated work per cycle, the work delivered over all stroke. For indicated power, it can be defined in formula form, where indicated power equal to W times crankshaft speed in revolution per second divided by number of crank revolution per cycle, where for 4-stroke it is equal to 2, whereas for 2-stroke is equal to 1. From the formula, we can say that power can be increased by increasing the engine size, the compression ratio, and also engine speed. Indicated work at part throttle. At wide open throttle, the pressure at the intake valve is just below atmospheric pressure. However, at part throttle, the pressure is much lower than atmospheric pressure. Therefore, at part throttle, the pump work, which is at area B and C, can be significant compared to gross indicated work, which is at area A and C. For indicated work with supercharging, engine with supercharged or turbocharged can have intake pressure greater than exhaust pressure, which give a positive pump work. Supercharged increase the net indicated work but add to the friction work of the engine. since they are driven by the crankshaft.
Hello, my name is Audra Laili binti Aung Jasni and my metric number is 63170. So today I'm going to explain about mechanical efficiency. Some of the power generated in the cylinder is used to overcome engine friction and to pump gas into and out of the engine. So the term friction power, which is denoted by the symbol WF, is used to collectively describe these power losses, such that friction power is equal to gross indicated power minus brake power. Friction power can be measured by motoring the engine. The mechanical efficiency is defined as brake power over gross indicated power, which is equal to 1 minus friction power over gross indicated power. So, mechanical efficiency depends on throttle position, engine design, and engine speed. Typical values for car engines at wide open throttle are 90% at 2000 revolutions per minute and 75% at maximum speed. Throttling increases pumping work and thus decreases the brake power, so the mechanical efficiency drops and approaches zero at idle. Power varies with speed, but torque is independent of engine speed. Let's move on to power and torque versus engine speed. So rated brake power, which is RBP, is a maximum in the brake power versus the engine speed. At higher speeds, brake power decreases as friction power becomes more significant compared to the indicated power, which is brake power is equal to, again, gross indicated power minus by friction power. There is a maximum in the torque versus speed called maximum brake torque, or MBT. Brake torque drops off at lower speeds due to heat losses, and also at higher speeds it becomes more difficult to ingest a full charge of air. Moving on to the indicated mean effective pressure, also known as the IMEP. IMEP is a fictitious constant pressure that would produce the same work per cycle if it acted on the piston during the power stroke. IMEP is equal to the indicated work over engine size, which is also equal to the indicated power times by the number of crank revolutions per cycle over the engine size times by the engine speed, in which the engine power is equal to IMEP times by the engine size times by the engine speed over the number of crank revolutions per cycle, which is also equal to IMEP times by the cross-sectional area of a cylinder times by the average piston velocity over 2 times the number of crank revolutions per cycle. IMEP does not depend on engine speed, just like torque. IMEP is a better parameter than torque to compare engines for design and output because it is independent of engine speed and engine size (VD). Brake bin effective pressure, also known as BMEP, is defined as BMEP is equal to brake power over engine size, which is also equal to 2 pi times by torque times by number of crank revolutions per cycle over engine size, in which torque is equal to BMEP times by engine size over 2 pi times by the number of crank revolutions per cycle. The maximum BMEP of good engine designs is well established. For 4-stroke engines, SI engines is around 800 and 1000 kPa, CI engines 500 to 900 kPa. For turbocharged SI engines, 1200 to 1700 kPa, and for turbocharged CI engine is 1014 to 1400 kPa. For 2-stroke engine, the standard CI engine is comparable to 4-stroke BMEP. For large low CI engines, it's around 500 to 1600 kPa with supercharging. The maximum BMEP can be used in design calculation to give estimate engine displacement required to provide a given torque or power at specified speed. Let's move on to the maximum BMEP. So the maximum BMEP is obtained at wide open throttle at a particular engine speed. Closing the throttle decreases the BMEP. For a given displacement, a higher maximum BMEP means more torque. For a given torque, a higher maximum BMEP means smaller engine. Higher maximum BMEP means higher stresses and temperatures in the engine, hence shorter engine life, bulkier engine. For the same BMEP, two-strokes have almost twice the power of four-stroke. So in this slide, you can see the typical 1998 passenger car engine characteristic in this table below.
Hello, my name is Cornelius. My matrix number 63152. Today I'm going to present on few subtopic related to basic engine operations and engine parameter. So let's go. So road load power or PR is engine power needed to overcome rolling resistance and the aerodynamics of the vehicles. So here is the important equations of road load power. So CR means the coefficient of rolling resistance, which range from 0.012 to 0.015. MV is the mass of vehicles. G is the gravitational force. Rho A is the ambient air density. Next, coefficient of drag. So for car, the value of CD is between 0.3 to 0.5. AV is the vehicle frontal area, and the last one is SV, which denote as the vehicle speed. So vehicle fuel economy is usually defined as MPG or liter per 100 kilometer. Fuel consumption testing is measured in terms of fuel mass flow rate, or denoted as M.F. So SFC, or specific fuel consumption, is a measure of how efficiently the fuel supplied to the engine to produce power. While BSFC, or brake specific fuel consumption, is a parameter that reflects the efficiency of combustion engine, which burn fuel and produces rotational power either at shaft or crankshaft. So in automotive, it is used to evaluate the efficiency of internal combustion engines. So the word brake is related to the use of dynamometer or electrical brake to evaluate the engine parameters such as engine mass flow rate, torque, and etc. So this equation uh, uh, represent the brake specific fuel consumption and also indicator specific fuel consumptions. So both of these equations have the same unit, which is gram per kilowatt hour. Next, brake specific fuel consumptions, or BFC, decrease with engine size due to reduced heat losses from gas to the cylinder wall. So this graph represents the relationship between BCFC against the engine displacement. So cylinder surface to volume ratio increase as the bore diameter increases. So it can be proved by this equation. So next, this diagram showing the BCFC versus engine speed curve. So what we can interpret from this diagram is that BCFC increase at high speed due to increased frictions. So it will result in smaller W.B. So next is BCFC also increases at low speed due to increased time for heat losses from the gas to cylinder wall or piston wall. Thus, it will resulting in smaller W.I. So the last one is BCFC increase with compression ratio due to higher thermal efficiency. So in this slide, from the previous one, we know that BCFC is equal to m dot f over w dot b. So to be more clearer, so BCF, this equation represent the basic relationship of brake specific fuel consumption, which is initially measured in kilogram per joule, and m dot f is measured in kilogram per second, and PE, which is effective engine power, which measured in kilowatts. So usually m dot f or fuel mass flow rate is measured in gram per second. The engine is in kilowatt, then we will get the final unit of BSFC in gram per kilowatt hour. So since engine power or PE is product of engine speed and torque, so we can express the BSFC equation in the function of engine speed and torque. So the next derivation for BSFC equation is BSFC equal to m dot f over omega e multiplied with TE. So TE is the effective uh, engine torque measured in Newton meter, while omega e is the engine speed, which measured in radian per seconds. So engine torque also defined as the function of mean effective pressure or MEP of the engine. So this is the derivation of uh, mean effective pressure or engine torque. So NC is the number of cylinder. It is a dimensional unit. So next is VD. VD is the cylinder displacement or volume, which measure in cubic meter. So PME is the mean effective pressure measured in Pascal, while NR is the number of stroke, also dimensional unit. So for four-stroke engine, NR is equal to 2. So this is the final equation for BSFC. So as we noted that the lower the BSFC or brake specific fuel consumption, the more efficient the engine is. So for spark ignition or usually gasoline engine, the BSFC value is around 250 gram per kilowatt hour, while for compression engine, the BSFC value is around 200 gram per kilowatt hour. So the use of performance map is to display the BSFC over the engine full load and speed range. So it just use the dynamometer to measure the torque and fuel mass flow rate. We can find the uh, brake mean effective pressure or BMEP, also W.B, and also the BSFC. So BSFC usually represent in a contour plot in the function of engine speed and torque. So on this diagram, the this arrow showing that this red dotted line showing that it is the full engine load or maximum MEP, while the second arrow showing the most efficient operating point of the engine. So that's all from me. Thank you.
Hello, my name is Christopher Limbert. My metric number is 63147. From this slide, the engine thermodynamics efficiencies. Whenever heating value of fuels are known, it is possible to determine the engine's thermodynamic efficiency. The table shown is taken from the worldnuclear.org, where the heat value of a fuel is the amount of heat released during combustion, also referred to energy or calorific value. Heat value is a measure of a fuel's energy density and is expressed in joule energy per specified amount, for example, kilograms. Combustion efficiency is a measure of how effective the heat content of a fuel is transferred into usable heat. From the formula, the efficiency is equal to actual heat input over theoretical heat input. As for the thermal efficiency, it is a percentage of heat energy that is transformed into work. For the first formula, the thermal efficiency is equal to work per cycle over heat input per cycle. As for in terms of rates, the thermal efficiency is equal to power out divided by rate of heat input. The thermal efficiency can be given in terms of brake or indicated value. The indicated thermal efficiency are normally 50 to 60%, and the brake thermal efficiencies are usually 30%. For the fuel conversion efficiency, it is the ratio between useful mechanical work produced by the engine and the theoretical energy content of the fuel mass. This is the given formula, which is eta F equal to W over mF times by Q of heating value of the fuel. Therefore, it can also be obtained from eta F equal to 1 over SFC times by QHV. Next is the volumetric efficiency, where it measures the effectiveness of an engine. From the formula, we can see that eta V is equal to actual air inducted divided by theoretical air. The typical values for wide open throttle WOT ranges from 75% to 90% and lower when the throttle is closed. When an engine is throttled, the volumetric efficiency will be less than 1. When it is running at full torque, volumetric efficiencies can be about 1. Lastly, the supercharged engines will have a volumetric efficiency more than 1. The volumetric efficiency is used in two ways. Firstly, it is used to measure the tuning effectiveness of the intake manifold and valve system, in which the volumetric efficiency functions as an indicator. For this purpose, the high condition would refer to the density at intake manifold temperature and pressure. The ideal volumetric efficiency would be around 1, and its actual volumetric efficiency would be reduced by flow losses at the valve, but it could be increased by pulsation tuning. Secondly, it acts to indicate how much mixture is flowing through the engine. The calculation is usually done including fuel or air mixture and with the reference density set at ambient temperature at ambient atmospheric conditions. As for the air-fuel ratio, which is AF, it is a ratio between the mass of air, MA, and mass of fuel, MF, used by the engine when running. This is the formula of the air-fuel ratio. An ideal AF is around 15 to 1. For SI engine, AF is in range of 12 to 18, which depends on its operating conditions. For the CI engine, AF is in range of 18 to 70, where the mixture is highly non-homogeneous. So these are the parameters. Firstly, the mean effective pressure MEP, brake specific fuel consumption BSFC, engine efficiency, volumetric efficiency, energy conservation for the first law analysis, and entropy conservation, second law analysis. MEP, mean effective pressure, which is the work done per unit displacement volume, which categorized as IMEP and BMEP. The first one is IMEP, indicated mean effective pressure, which is the net work per unit displacement volume done by the gas during compression and expansion. BMEP is the brake mean effective pressure based on the external shaft per unit volume done by the engine. So these are the formula based on the top for 4-stroke and 2-stroke engine. For the volumetric efficiency is based on the mass ratio, and for 4-stroke engine, this is the formula. And for the direct injection engine, it is equal to m dot f equal to 0. And finally, the energy conservation, which is the net energy passing the control surface, is either stored or depleted from the controls volume for a system open to the transfer of enthalpy, mass, work, and heat. Secondly, the entropy conservation, which takes into account the irreversibility that happens in each process, the development of usefulness of each type of energy, which is known as exergy. That is all from us. Thank you.